Hi, and welcome back. Okay, so today we're going to talk about alternating series. What is an alternating series? Well, an alternating series is a series whose terms are alternately positive and negative on consecutive terms, okay? So here we have 1, negative 1/2, 1/3, negative 1/4, da-da-da-da-da. That's an alternating series. So this would look like the sum from 1 to infinity of negative 1 to the n plus 1 power times 1 over n. And I guess you could also write that as like the sum from n equals 1 to infinity of negative 1 to the n plus 1 power over n. That's the same thing, right? Here we've got negative 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial. Well, that's the same as n equals 1 to infinity of negative 1 to the n times 1 over n factorial. And again, this could also be rewritten as negative 1 to the n over n factorial. That's the same. So you can see here this negative 1 to the n plus 1, that gives us an alternating series. Negative 1 to the n gives us an alternating series. And then the other typical one would be negative 1 to the n minus 1. That would give us an alternating series. There is another one that we'll talk about as we go on, but basically these are, these are alternating series. So this is it. And we actually have a test for alternating series. So if a sub n is greater than 0, then the alternating series, the sum from n equals 1 to infinity of negative 1 to the n times a sub n, or from 1 to infinity of negative 1 to the n plus 1 a sub n, and it could be this one too, to the n minus 1, converges, so it converges if both of the following conditions are satisfied. The limit as n approaches infinity of a sub n equals 0, and a sub n is a decreasing, or you could say non-increasing sequence, where that a sub n plus 1 is less than a sub n for all n greater than k, for some k contained within z. I think those are a natural number, real numbers, whatever. Well, let's look at this first condition here. The limit as n approaches infinity of a sub n equals 0. That's just the nth term test, right? The nth term test for divergence, which of course should be done first when you're using these tests, and we will continue to use on and on and on again forever. Okay, so let's do a few examples here. We're asked to determine whether the following series converge or diverge. So we have the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over 2n minus 1, okay? Well, first thing we're going to do is find the limit as n approaches infinity of n over 2n minus 1. Well, what does that equal? That equals 1/2, which does not equal 0. So it does not equal 0, so it must not converge. So it diverges. So the series diverges by the nth term test, right? This is the nth term test because we didn't do both parts of the alternating series test, right? And we did just the nth term test first. All right, let's do another one. N equals 1 to infinity of negative 1 to the n over n times, this is the natural log of 2n. So we're going to take the limit as n approaches infinity of n over the natural log of 2n. And that equals, or you're going to have infinity, or, well, it's just going to be infinity, right? Which does not equal 0. So the series diverges by the nth term test again. Okay, let's see if we can get one that actually converges here. Right? Here we have the sum from 1 to infinity of cosine of pi n over n. All right, so this is one I want to talk about. If we're looking at this, what's the behavior of cosine? Well, cosine, if I plug in a value, right, if I have, like, put in 1 here, we're going to have cosine of pi is going to be negative 1. Then cosine of 2 pi is going to be 1. Then cosine of 3 pi is negative 1. Then cosine of 4 pi is 1, and on and on and on forever. So this is that hidden oscillator that I talked about earlier, and sine as well. So if I had sine of like pi n over 2, that also would be a hidden oscillator that would make this an alternating series, right? On and on and on and on and on. So then if this is the alternating part, we actually have a 1 here, and so we can look at 1 over n, and that's what we're going to find our limit of. So the limit as n approaches infinity of 1 over n. Well, we know that that equals 0, right? And is this decreasing? And, yep, 1 over n is decreasing. So the series converges by the alternating series test. Okay, I think this is kind of interesting because this is actually the harmonic series, but it's not a series here, right? It's the limit. So even though it's so similar, it's actually converging. So very cool. All right, here the sum is n equals 1 to infinity of negative 1 n to the negative 1 over n factorial. All right, well, let's find our limit here. So the limit as n approaches infinity of 1 over n factorial, that's going to equal 0. And is it decreasing? Well, n factorial, you'd have 1 factorial, 2 factorial, 3 factorial. Yeah, that's going to be decreasing. And that's decreasing. Oops. So the series converges by alternating series test. Okay, let's do a few more. Here we have the sum from 1 to infinity of negative 1n over n minus 5 squared plus 1. Well, I'm going to find my limit. Oh, sorry, kids, I keep yawning. As n approaches infinity of 1 over n minus 5 squared plus 1. You know, if I expanded that out, I'd have an n squared, which is just, anyway, this is going to become 0. And it does decrease, right? It's going to get smaller and smaller and smaller. So the series converges by alternating series test. Notice that I'm writing this out, because if I just put AST, that's not like an accepted abbreviation in calculus. So I don't want you to miss anything on the exam. All right, and what about this one here? Well, we kind of already dealt with this, right, when we dealt with cosine earlier. So this is going to be the limit as n approaches infinity of 1 over n. We know that equals 0. And this is decreasing, so the series converges by the alternating series test. Okay, so let's talk about two kinds of convergence that we have. We have absolute convergence and conditional convergence. All right, so we have theorem here. If the series, the absolute value of the series converges, then I should put this and this also converges without the absolute value, then they are absolutely convergent. If this converges, but the absolute value diverges, then it's conditionally convergent. So let's look at a few examples of that. Here, we're given the sum from n equals 1 to infinity of negative 1 to the n over the square root of n. Okay, so we're going to find the limit as n approaches infinity of 1 over the square root of n. Well, that's just going to be equal to 0, right? And this does decrease, and this decreases. So this converges by what am I saying here? Alternate series. Good, alternating series test. Gosh, total brain fart there for a minute. So let's find out, well, let's look at this without the absolute value, right? So the sum from n equals 1 to infinity of 1 over square root of n, right? Let's look at that. What's that going to be? That's going to be a p-series. That's a divergent p-series, right? That's a divergent p-series because p is equal to 1/2, and the absolute value of that is less than 1, right? So the series n equals 1 to infinity of negative 1 to the n over the square root of n is conditionally convergent, right? It's conditionally convergent because this and this is the absolute value of that, right, are not the exact same. This one converges, this one diverges. So it's conditionally convergent. All right, let's do another one here. The sum from 1 to infinity of negative 1 to the n plus 1 over 3 to the n, okay? Well, if I take the limit as n approaches infinity of 1 over 3 to the n, that's going to be equal to 0, and this does decrease. And this decreases, okay? So this converges by the alternating series test. My handwriting is getting worse as I go on here. All right, so now let's deal with the absolute value. We've got the sum from n equals 1 to infinity of 1 over 3 to the n. Well, to me, that looks like a geometric series. I could rewrite that as 1 to infinity of 1/3 to the n, right? And so this is going to be a convergent geometric series because 1/3, the absolute value of 1/3 is less than 1, right? So the series is absolutely convergent, right? It's convergent here, it's convergent here. It's absolutely convergent. All right, one last thing I want to discuss with these alternating series tests. We want to talk about alternating series remainders. So if an alternating series satisfies the conditions at the alternating series test, right, so it's convergent, then the series has a sum s. That makes sense, right? If it's convergent, it has a sum. Then the remainder of n is equal to s minus s sub n, that partial sum, which is less than or equal to a sub n plus 1, where s sub n is the nth partial sum of the series, and this a sub n plus 1 is the next unused term, okay? I'll just write that there. The next unused term. Okay, so let's actually do this. Approximate the sum from 1 to infinity of negative 1 to the n minus 1 over n factorial by using the first 6 terms and find the maximum error. Use the results to find an interval in which s must lie. Okay, let's actually do this on our calculator. So first we're asked to use the first 6 terms, so we're going to find s sub 6. Okay, so s sub 6, I'm going to go to math. Oh, no. I'm going to go to alpha window 2, and I'm going to use x's even though there's n's. That's okay. And I'm using the first 6 terms of, and actually something you can do here, you can do, I think it's alpha window. Nope. Second window? Nope. Alpha F1. Yeah, there it is. It's alpha y equals. And if I press 1, now I can actually write this as a fraction. So I've got negative 1 to the n minus 1. So I'm going to do x minus 1, because again, it doesn't matter what your variable is, over x factorial. So x, and then factorial is math PRB. Okay, and I hit equals. I get 91 over 144, which equals 0.63194444. Okay, and I'm going to store that. Oh, I forgot to write that. Anyway, store as alpha A. Okay, I'm going to say that that's equal to A. All right. Now I want to find. So my remainder, r sub 6, I know is going to be less than or equal to my next unused term. Well, my next unused term is going to be a sub 7, right? And a sub 7 is going to equal 1 over 7 factorial. That's a 9, even though it looked like an A. 7 factorial, which equals 1 divided by 7, math 4. Okay, so that's going to equal 0.000198, and I'm going to store that as B. Okay, so store alpha B. Okay, so now what I didn't write here is that our error S, our error S must lie within S sub n minus R sub n and S sub n plus R sub n. Okay, so that's what our error has to actually lie within. And now I can use all of this information to write the interval that S must lie in. So my interval S must be contained within, and I'm just going to have A minus B comma A plus B. And if I actually put that in my calculator, right? If I put that in my calculator, I get, so alpha A minus alpha B and alpha A plus alpha B. And you can see these are really similar to one another, so I would write a lot of decimals here. I would definitely write more than 3. 0.6314117. 7460, 0.6321428. Okay, I'd write quite a few. So there's an interval. It's pretty small. It's pretty narrow, but the error between it has to be between these two numbers, right? Okay. So let's approximate the sum of n equals 1 to infinity of negative 1 to the n plus 1 over n to the fourth with an error less than 0.001. Okay, so we need to find out our a sub n plus 1, the absolute value of that, needs to be equal to 0.001 or less than that, right? So our n plus 1 is what we're trying to find. Good? So let me pause here for a second. Okay, well our a sub n is equal, basically to like this 1 over n to the fourth. So that's what I want to be testing out here, okay? So if I go 1 divided by 1 to the fourth, well, that's not really anything. 1 over, oops, clear. 1 divided by 2 to the fourth, that's not small enough. 1 divided by 3 to the fourth, not small enough. 4 to the fourth, not small enough. 5 to the fourth, so close, but not small enough. 6 to the fourth is definitely going to be small enough. That's going to be an error less than 0.001. So my n plus 1 is equal to 6, so n is equal to 5. Okay? So now I can approximate that sum with less than that error. So S sub 5 is going to equal, and I'm going to use my calculator again. So math window, oops, second quit. Alpha window, 2x 1 to 5 of alpha y equals, and I have negative 1 to the x plus 1 over x to the fourth. And I set enter equal, so I get 0.947539429. Okay? So that's within the actual, that is within, oops, within 0.001 of the actual sum. Okay? Pretty accurate, pretty cool. Okay, any questions, leave them in the comments, and I hope I get to see you soon. Bye.